Let's do one more example using term symbols. Given the ground state electron configuration of carbon, what are the possible term symbols for carbon? Let's start with the ground state electronic configuration of carbon. Carbon is a 1s2, 2s2, 2p2. These are completely filled shells here, so these do not contribute to the angular momentum. Therefore, we only have to worry about the p electrons. So remember, for each electron in the carbon 2p, little s is equal to 1/2, and little l is equal to 1. It's a p electron, and each electron has a s1/2, s equal 1/2. So let's find what capital S is, the total intrinsic spin. That goes from S1, first electron, plus second electron, down to the difference, absolute value of the difference between S1 and S2. In this case, both S's are 1/2, so big S can go from 1/2 plus 1/2, or 1, to 1/2 minus 1/2 is 0, and go from 1 to 0 in integer steps, so the only two values there are 1 and 0. Let's look at capital L. That will be equal to the little l1 plus l2 in integer steps to the difference between the two. L1 is 1, L2 is 2, so this can go from 2 to 0 in integer steps, so L can be 2, 1, or 0. Now if we just blindly go ahead and say, okay, let's look at various combinations of this, the L equal 2 will be a D term symbol, and the S equal 1 to S plus 1 is 3, so this will be a triplet. The L equal to S equals 0 will be a singlet D. Similarly, this is P, be a triplet P, and a singlet P, and a triplet S, and a singlet S. So we would think first off, we just blindly apply this rule, there would be 6 term symbols that we can associate with the ground state of carbon. However, let's look more carefully at some of these. Let's look, for instance, at 3s. What does that mean? Well, the 3 means S is equal to 1, and the S means, not to be confused with that S, that's a different S here, that S means that L, big L, is equal to 0. Now, how are you going to arrange 2 electrons in a 2p orbital to get a 3s, S equal 1, L equals 0? Well, just let's see if we can do that. Here is m sub L equals, say, minus 1, 0, and 1. In order to get big L equals 0, both electrons are going to have to be in the L equals, or m sub L equals 0. And to get S equal 1, they're going to have to be parallel spins. They can't be paired. So this would be the only way you can get a 3s, a triplet S, from 2 electrons in the p orbital. This violates the Pauli exclusion principle. So in fact, even though you can write this down, it's not possible because you can't violate the Pauli exclusion principle. However, let's take another look at this. Let's suppose we had not only the 2p, but also we had the 3p. So now we have some excited state of carbon where we've taken one of the electrons from the 2p and gone up to the 3p. Here we can have both electrons with parallel spins, and here big L is equal to 0. We make m sub L equal minus 1, 0, and plus 1. We can put both of them there to make L equal 0, and S here can be 1, or in other words, you can have a triplet S state if the electrons are in different energy states given by a different principal quantum number n. Because you put parallel spins here, since n is different, this electron will not have the same 4 quantum numbers as this electron, and therefore for an excited state you can have this. So this is okay if n is different. So you can have 2 electrons with, for example, m sub s equals minus 1/2 or plus 1/2, and at the same time L is equal to 1 if n is different. Only if n is different. All right, well, what can we do? Well, we can sort of go through all of these and try to figure out which is allowed and which is not. But there's another approach, and that's called the microstate approach. And what one does here is write down all possible combinations of the electron intrinsic spin and the angular momentum. In other words, all possible combinations of m sub s and m sub l, and then figure out what term symbols correspond to those. So let's go ahead and do this. Let's say m sub l is equal to, say, minus 1, 0, and plus 1. And we'll make a column here of possible values. And let's say alpha is m sub s equal plus 1/2. And let's use beta to be m sub s equal minus 1/2. All right, well, just go blindly and start filling in all possible combinations of m sub s and m sub l. We could put two alphas here. We could put an alpha here and an alpha here. Alpha here and an alpha here. We can put two alphas here, or you put one alpha here and one alpha here, or two alphas here. So these 1, 2, 3, 4, 5, 6, these are the only 6 combinations we can get when we have both electrons having the alpha spin. And let's figure out big M sub L and big M sub S for each one of these combinations, what the possible values of M sub L and M sub S are. Well, here they're both minus 1, so M sub L here is minus 2. Here, one is minus 1 and the other is 0, so M sub L here is minus 1. Here, 1 and minus 1, they cancel each other out. Here, both are 0, that'll be a 0. Here is 0 and 1, so the M sub L here will be plus 1, and here it'll be plus 2. M sub S, since they both have M sub S equal plus 1/2, big M sub S will be 1 for all of these. Let's look at another combination. Let's say M sub L equal minus 1, 0, and 1. Let's look at the combination of alpha and beta. One spin up, one spin down. Well, we could put an alpha here and a beta here. Now we can switch them because they're two separate ones. This will be a beta and this will be an alpha. We can put an alpha here and a beta over here. Or we can put a beta here and an alpha over here. Let's put an alpha beta in the middle here. We can put an alpha here and a beta here. Or we can put a beta here and an alpha here. And here we can make an alpha beta. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 different ways to arrange the alphas and betas among these three units. Let's see what M sub L and M sub S will be here. M sub L, we got 2 minus 1, so this will be a minus 2. Here we have a 1, a minus 1. Here we have, again, a minus 1. Here, a minus 1 and a 1, that's a 0. This will be a 0. Both of these are in the 0, so that'll also be a 0. Here we have alpha and beta, 1 and 0, 1 and plus 1, so this will be a 1. That'll also be a 1. Here they're both in the plus 1, so that'll be a 2. For each one of these, we have M sub S plus 1/2 and minus 1/2. They'll cancel each other out. So each one of these, since it's an alpha beta, will be M sub S equal 0. And then finally, we have the combination where they're both pointing down. Let's put beta beta. That's both pointing down. We'll put a beta there and a beta there. A beta there and a beta there. 3 combinations. Put 2 betas here. And put 1 beta here and 1 beta here. And then put 2 betas here. 1, 2, 3, 4, 5, 6. Let's count up M sub L and M sub S for each one of these combinations. M sub L, minus 2. Here's minus 1. Here's 0. That's also 0. 0 plus 1 is 1, and 1 plus 1 is 2. M sub s, as we're both pointing down, M sub s will be minus 1 for all of these. Now let's go and see what kind of things we can cross out using the Pauli exclusion principle. Let's start here. This is spin pointing down, spin pointing down. Both values here have M sub s equal minus 1/2, and they're both in here. So you can't have both spins pointing down for a particular subshell here. So we can get rid of this. This violates the Pauli exclusion principle, as does this. You can't have two electrons having the same quantum number. That also be canceled out. If we took a look at this, well, that's okay. So we have M sub s equal plus 1/2 and minus 1/2. No problem there. Here we have the same kind of problem. Here both spins are pointing up, so we get rid of that for the Pauli exclusion principle. Violates the Pauli exclusion principle. All right, let's take a look at what we're left with. Here's values of M sub l, M sub l, M sub s. Here's some here that we're allowed. Well, let's see what we can make out of this. This is M sub l minus 2, minus 1, 0, 1, and 2. For M sub l going like that, that seems to indicate we have a capital L equal 2, because M sub l can go from minus 2, minus 1, 0, plus 1, plus 2, if capital L is equal to 2. So one of our term symbols is probably a D, all right, because M sub l goes from minus 1 to plus, minus 2 to plus 2 in integer steps. Let's take another look at that. And it looks like for each one of these, M sub s is equal to 0. So if we want to write a superscript on that, that'll be 2s plus 1, or it'll just be 1. So it looks like that's one of the term symbols. So let's go back out here. But first let's get rid of somehow this there. Okay. So let's go up here. And M sub l, we start crossing these things out. We've taken care of this one. Minus 1 and 0. So M sub l equals minus 2, minus 1. There's 0. M sub l equal plus 1, 0. And M sub l equal plus 2, 0. So we've taken care of these 5 possible combinations of alpha and beta and M sub l and so on with our term symbol singlet D. Now let's take a look at what's left over here. Let's look at M sub l. M sub l is minus 1, 0, plus 1 here. Looks like minus 1, 0, plus 1 for M sub l there. Minus 1, 0, plus 1. I bet if L is equal to 1, then M sub l minus 1, 0. So it looks like we have a P in that mishmash there. And let's see what kind of multiplicity that would have. Looks like M sub s is a minus 1 here. M sub s is 0, and M sub s is 1 here. Well, if s is equal to 1, then M sub s could be 1, 0, and minus 1. So it looks like that this is going to be a triplet P. Let's see what we can cross out with a triplet P. A triplet means that s is equal to 1, so M sub s can be minus 1, 0, or plus 1. And for L is equal to 1, that's what that P means. M sub L could be minus 1, 0, and plus 1. So let's start crossing these things out. Let's do the M sub L equal minus 1, and then cross out the M sub S minus 1, 0, and plus 1. So we're looking for all the ones that have M sub L equal minus 1. Here's M sub L equal minus 1 with a minus 1. Here M sub L equal minus 1 with a 0. And here M sub L equal minus 1 with a 1. So we crossed out the M sub L equal minus 1 with those 3. Let's look at M sub L equals 0 with M sub S equal minus 1, 0, and plus 1. So we're looking for M sub L equals 0. And there's an M sub L equals 0 and a minus 1. M sub L equals 0 and a 0. And M sub L equals 0 and a plus 1. So that's that one there. So we've done m sub l equals 0 with those three. Now let's do m sub l equal 1 with those three. M sub l equal 1 with a minus 1. M sub l equal 1 with a 0. And m sub l equal 1 with a plus 1. All right, so we've crossed out all the possible combinations corresponding to a triplet P. And what do we have left over? Well, we crossed out all of those. Oh, look, there's one left over here. M sub l equals 0, m sub s equals 0. And we crossed out all of those. We just have one term symbol left to account for this. M sub l equals 0, m sub s equals 0. Well, that's a singlet S. So these are the only three term symbols that are allowed for the ground state of carbon. Well, let's start thinking about the D, the J. So 1D, this implies that S equals 0 and L equal 2. So this implies that J can go from S plus L to S minus L in integer steps, and that's just J equal 2. Let's look at the triplet P. The triplet P means that S is equal to 1 and J is equal to, let's see, P, J is, sorry, not J, L. L is equal to 1. So this means that J can go from S plus L, 2, down to the S minus L, which is 0, in integer steps, 2, 1, and 0. And let's look at the singlet S. This implies that S is equal to 0 and L is equal to 0. That means that J is equal to 0. So, with the J values, these are possible term symbols for the ground state of carbon. We have a 1D2, we have a 3P2, 3P1, 3P0, and a 1S0. But wait, there's even more. Let's look at the values of M sub J. So for a 1D2, possible values for M sub J, it can go from minus J to plus J in integer steps. This could be minus 2, minus 1, 0, plus 1, and plus 2. Let's look at the triplet P. So now, just in introductory chemistry, there was just the 2P for carbon. You had, well, maybe we'll just draw it this way. The way we did it in introductory chemistry. Just this degenerate p orbitals. We had one electron there and one electron there. Now, what we have are these energy levels. We have 5 energy levels. Let's see if we can figure out what the ground state is. The ground state, maximum multiplicity, so that'll be the 3. Then we have maximum L. Well, they all have the same value of L. We have the minimum value of J. So this will be a 3P0. We can't use Hund's rule to figure out what the next level is, but the next level is 3P1. The next level up there is 3P2. Then comes the 1D2, and finally we have the 1S0. So there's the 5 energy levels, and it's a little more complicated because this D level is a 5-fold degenerate, 1, 2, 3, 4, 5. The one singlet, that is there. This one is a 5-fold degenerate, and this is 3-fold degenerate, and this is 1-fold degenerate. So it's a little more complicated than we first thought for introductory chemistry. We have all these energy levels, and that's simply because of spin-orbit coupling, Russell-Saunders coupling. So that's pretty involved. Now, carbon, write down the possible term symbols for carbon. That's what everybody does. All the introductory chemistry texts do that. And also, if you go to the Wikipedia article under term symbols, you have actually a fairly nice, concise write-up on how to get term symbols using the microstate approach. And the Wikipedia article, I checked it out, seems to be okay. So if you want to review the Wikipedia article, look up Wikipedia term symbol, and you'll have the same kind of thing. If you look in any introductory chemistry text, like Atkins, they'll also do the same kind of thing. There you have it, term symbols.